Good morning, everybody. I'm Sourabh Mukherjee, Executive Vice President, Strategy and Sustainability for Tata Projects. I welcome everybody to the Carbon Reduction Electrification stage here at India Energy Week 2026. I have the pleasure of inviting Lisa. Lisa is the licensing manager from Johnson Matthey, Davy Technology Limited, one of the global leaders in a lot of technologies. She will be talking how Johnson Matthey is helping global customers reach their decarbonization path. She has worked in process plants, operation, process design and commissioning, and has spent several years in academic research and operation and strategy. Lisa, over to you.
Morning, everyone. My name is Lisa Weirs, and I'm delighted to be here on behalf of Johnson Matthey Technologies. Today I'll be talking about synthetic methane, or SNG. I'll be exploring the technology itself, its benefits, and how it could contribute to helping India meet its ambitious decarbonisation plans. I'd just like to start off with a brief introduction to Johnson Matthey. We were founded in 1817, so we've been around for 200 years. We've got a very long history in developing cutting-edge technologies for our clients. We have about 10,000 employees worldwide, and about 1,800 of those are based in Catalyst Technologies, which is where our methanation technology sits. We have 100 years of history in methanation technology itself, so we're very well positioned to work with our clients. Just a brief introduction on synthetic methane and why we feel it's the flexible energy vector. It can be produced from a number of different feedstocks. So gasification from coal produces syngas, which is a feedstock to produce methane. Biomass or waste that's gasified, and also from green hydrogen, any captured CO2. Methanation technology itself has been around for decades. It's a proven technology, it's very reliable, so it can integrate well with upstream and downstream processes. Methane itself is very high energy density and highly efficient. And as a gas, it's easily storable and very transportable. And probably the most important part as to why it's such a flexible energy vector is that it can be dropped into existing infrastructure. So you don't need to wait for new policies and funding. There are 3 different flavors of product of SNG, or methane, and these align very well with the national missions that have been set out by the Indian government. So the coal gasification mission, which is aiming to gasify 100 million tonnes by 2030, the syngas produced from coal gasification can be used to make methane, and this can either be used for electricity, it can be dropped into national grid pipelines, it can also be used as a feedstock for high value products such as chemicals and fertilizers. E-methane, which is produced from green hydrogen, so the green hydrogen mission, which has been run by the Indian government to promote domestic electrolyzer and hydrogen production, is really important in terms of long-term decarbonisation solutions for e-methane. There's also the bioenergy mission, which could contribute very well from using biomass and waste feedstocks. Just taking a closer look at the production of green methane in India, so that the costs of green hydrogen production are very high at the moment, and these are the rate limiting factor in terms of production of e-methanation at scale. So the International Energy Agency is tracking just over 2 million tonnes of announced hydrogen capacity by 2030. So this is against a target of 5 million tonnes. So it just shows the impact of the high costs of producing that green hydrogen. Current estimates for green hydrogen costs in India at the moment indicating a range of 3.5 to 5 US dollars per kilogram. But with the opportunities being offered through policy and innovation, the IEA predict that these costs could be reduced by about 1.8 US dollars per kilogram. So this would mean that you could produce e-methane at an indicative cost in the range of about $25 to $40 per MMBTU. So this makes it, over the longer term, a more viable and scalable opportunity. Having a bit of a focus on biomethane, India has massive biomethane potential. You might be able to see on the schematic, we have the typical industrial-sized, large-scale gasification from waste or biomass to produce syngas, or you also have your decentralized, smaller biomass, things like crop residues, animal manure, and by anaerobic digestion can produce biogas, which can then be sent on to produce methane, or it could be used to produce biogenic CO2, which can be used in the larger scale biomethane production. It reduces the carbon intensity on your feedstocks. Another option for the coal industry could potentially be topping up the feedstock with green hydrogen to continue the decarbonisation journey of the coal industry. I'd just like to introduce now our JM methanation technology. As I mentioned, we've been in methanation for over 100 years. It first started with our CRG catalysts that were first developed in the 1960s. These catalysts were then used with our flow sheet to produce town gas plants that were based in the UK, Japan, and Hong Kong. And then we went into the mid-80s where the first CRG catalyst was used in coal to gasification. This was in the US, the Dakota gas plant. And then into the early 2000s where we've licensed numerous coal to SNG plants in China and Reliance here in India. We've also got a very wide range of plant reference sizes. So from 18 kilotons per annum up to 1400 kilotons per annum. So we have a very scalable design. And then we move on to our flow sheet that's developed today into our Davy power gas, which is for use in the emerging e-methane market. I'm just going to touch briefly on the chemistry for methane. So the serum methanation line is your typical traditional coal to SNG chemical reaction. It's highly, highly exothermic. The CO2 methanation reaction is still exothermic, but a more mild exotherm. So this is what you tend to see from your green hydrogen biogenic feedstocks. There's also a reverse water gas shift reaction that will also happen at the same time to convert all your feedstocks to methane. And this happens across our catalyst at the same time. We have something called the M value, which is a stoichiometric ratio of the reactants of the feedstocks. And we tend to aim for an ideal value of 3. So if you have a higher value than 3, then in your product you would have a higher hydrogen content. And if the M value is lower than 3, then you would have more CO2 content. So we're able to vary that stoichiometry to meet the needs of the clients and the product compositions that are required. So in terms of what we offer as a licensing company, we have our flow sheet, but we also supply our catalyst. As discussed, our CRG catalyst has been proven over many decades, and we've got track record of our performance in the syngas methanation in those very extreme exothermic conditions. The catalyst itself is highly active and it's very thermally stable, and we've got lots of examples where we've had long catalyst life. We've also done extensive testing and R&D work to demonstrate the use of the catalyst in the CO2 methanation, and we've also been able to demonstrate outstanding performance. So the catalyst itself is able to deal with a very wide temperature range in the process. What you can see on the slide now is an example of our flow sheet. So it's made up of two main phases. So bulk methanation followed by trim methanation. There's a feed gas inlet with the feedstocks and also a recycle from the first stage bulk methanator. What you see is a typical example of an arrangement, but there might be more stages in the bulk methanation, or there might be more or less stages in the trim methanation. Again, it depends on the final composition requirements of our clients. It's a very scalable technology. As discussed, we've got reference plants over a wide range of plant capacities. The reactors are fixed bed adiabatic reactors to help counteract the exotherm. It's a very reliable and efficient process. It isn't made up of any specialist equipment, so your long lead term items are not as long as some other processes, so you can get to plant construction much faster, and it also allows for lower capex and a lower opex. So we feel that our technology can reduce your deployment risks and maximize the bankability of your projects. The other important factor about our technology is that it can integrate easily with upstream and downstream processes. So for example, on our methane Davy power gas process, the technology can support fast ramping and intermittency from the variability that you see in terms of renewable feedstocks. So this allows the reduction of hydrogen storage requirements so it can optimize the design. Likewise, with the downstream processes, it can fit in very well with LNG units. So again, reducing your capex and opex. We're also able to adjust as I mentioned earlier in the chemistry, the M value. We can change the stoichiometry. So for example, LNG pipelines have very tight specifications. If we need to remove excess CO2, we can do that. We're also able to provide pure spec adsorbents, so we can help with CO2 purification of the feedstocks and also on the product, so we can remove excess hydrogen, CO2 or water. It also generates steam, so that can be used for power generation or general heat integration with other processes. We can tailor the steam requirements. So we're able to optimize product and feedstocks to meet project requirements. And just to conclude, our Davy technology, we've got the proven catalysts in the traditional syngas and CO2 methanation. We're able to maximize the process efficiency from our decades of experience and our high quality heat recovery. We can integrate with upstream and downstream processes seamlessly. We have lower capex and deployment risks. The design is scalable, so we can deal with smaller or larger plants. We have the decades of experience and track record, and our operating model is that we can tailor our engineering design based on your project execution requirements. We could supply the catalyst, and we also provide technical services, so we can be with you all the way through detailed design, commissioning, operation, and through the lifetime of the plant. And we really, really value our long-term, deep relationships with our clients. And that concludes my presentation for today. Thank you for listening, and thank you for your time.
Thank you. I have the pleasure of introducing, and I hope I spell you right, Estela Vázquez Esmerode. That was close? Okay. So she's based in Copenhagen. She's the head of Program Energy and Fuels, Mærsk, McKinney, Møller Center for Zero Carbon Shipping. The hub seeks to provide industry guidance on what fuel qualify for decarbonization on the maritime industry and to catalyze industry actions to make those fuels and energy forms available for shipping. Uh, Estela has led carbon capture and storage projects and has worked with the development of green technologies before joining the quest for decarbonizing the shipping industry. Estela, the stage is for you.
Hello, everybody. Can you hear me? Good. So thank you very much. Thank you for inviting me to join today. My name is Estela, and when we hear about India, we hear about energy security. There's also a very big opportunity for actually export of products that can decarbonize some of the most hard to abate industries, which the maritime industry is one of those. So today I'm going to be presenting some of the work that my organization is doing about it, and then how we are engaging with a lot of Indian public and commercial actors. So just to start, a very brief introduction to the center that I'm representing. We are called the Mærsk McKinney Møller Center for Zero Carbon Shipping, and we are not for profit. We are independent and science-based. We've actually been funded by the family behind the Mærsk family. So we've been funded with $135 million as a philanthropic fund for the center to be created with the sole mission of supporting the industry towards decarbonization. So this is a question that we get very often, is how we're related to the company Mærsk, and this is why I'm bringing these slides to start with. So we are essentially, like I say, not for profit, and we are not connected to the commercial parts of the A.P. Møller holding, where you will, you know most of the companies underneath here, amongst them Mærsk. What I have to say is, obviously, Mærsk is one of our partners in our center, along with many other very big industry players. So why is it important for shipping to decarbonize at all? So there are around, when we are talking international shipping, there are around 100,000 vessels operating in the world, consuming 300 million tons of fuel and contributing to 3% of global emissions. And as we know, this contribution and where the trade growth that we are seeing is only expected to increase. In this graph, what I'm showing is the do-nothing scenario with trade growth. We expect the emissions from shipping will increase through the years. There are, of course, some initiatives in place. We see some energy efficiency going into the strategies, the shipping strategies. We see some regions applying regulations to reduce emissions. But in reality, this is not enough to achieve the goals of the maritime industry, also stated by the IMO in their greenhouse gas strategy in 2023, with an ambition to get to net zero by 2050. So something needs to be done. And there's limitations to what you can do from an energy efficiency perspective. You can reduce your emissions to some degree, but in reality, it is a fuel switch that is needed from fossil-based fuels to greener fuels, amongst them electrofuels like hydrogen, ammonia, and methanol. So one of the challenges that the shipping industry is facing is that these fuels are much more costly than the baseline. Shipping uses the base of the barrel kind of fuel, very on the spot market, and suddenly we need to switch that with very costly products, which is why there needs to be some sort of rethinking of the system in how to enable this fuel switch. And this is where green corridors come in. Green corridors are maritime routes where the vessel is supposed to use low carbon fuels. They are ring fenced, so they are trying to include the entire value chain, including the fuel producer, the port, the vessel owner, the cargo owner. So the entire value chain comes together in these ring-fenced projects to assess what are the challenges, how can they be overcome, how can the risk be shared across the entire value chain to make sure that we can execute on these projects. So it is very much a collaborative effort across the value chain. The center has been working with green corridors for the past 4 years. We've had some of the most advanced green corridors in the world. We've worked with Chile in several green corridors, South Korea. So we are quite widespread. And the reason why we are doing this is because we actually have put a lot of effort in developing a methodology that is pretty sound and robust in being systematic and data-based. So in our methodology, we kind of bring together the different actors from the value chain and assess the specifics of a country from an energy perspective. So what are the energy and fuel projects that are available or in the plan? From a ports perspective, what ports are suitable, because they already have some sort of capabilities within chemical product treatments and stuff. We also look into trade routes, cargo, and we look into regulation. So when it comes to regulation, it's not just the global regulation that applies here, but also regulation on a regional basis, on a local basis, and on a port basis. So when we get all this work together, we create what we call the data cube. And with this data cube and applying some success criteria, some selection criteria, we get a preliminary list of potential green corridors for this particular region. So now I'm going to show what we are currently doing in India. Last year, the ministries of Denmark and India met, and it was the Ministry of Port Shipping and Waterways that met with the Danish Ministry of Infrastructure and agreed that they wanted to pursue a further alliance when it came to green shipping. And they wanted to conduct this pre-feasibility study in India. So then the center was asked to take the leading role of this study, and we established this initial consortium. So we would have the Danish Maritime Authority, the Danish Energy Agency, but we also have the Indian Port Association and DG Shipping involved in developing this study. So each of these companies or public actors will take the lead in one of the specific work streams of the project. And we started this project before the year end, before end of 25, and we are currently conducting it. So I'm just going to show you, like very preliminary results of this. When we look into the work stream 2, which is energy projects in India, we do a proper mapping of what are the projects that are currently in the pipeline, from more mature to less mature, but we try to do an assessment of what are the projects that are in the pipeline and what type of fuels, the volumes, the commercial operation date. On the next work stream, we look into ports. Here is a list of 14 ports that have been identified so far, 13 of them public and one private port. And when we look into the ports, we not only look at their location, but also we look into their infrastructure, what they already have. So it could be cranes, it could be storage facilities, it could be many things. But we do a screening of potential interesting ports for the green corridors. Next, we look into, well, I'm saying next, but in reality, this runs in parallel, of course. We look into vessel and trade activities. So when we're looking into the different segments of vessels, like containers, tanker bulk, but we also look at passenger vessels, and what are the activities, or what's the potential of decarbonization of these different segments and routes. So we do also a mapping of this that we can put into our data cube. And finally, we also look into regulation. So when I said before, it's not only about global regulation, which could apply for international shipping, but it's also regional, like for example in the EU, or it can be national regulation, but it can also be local incentives and even port subsidies. So we look at all the different levels of regulation that can support the different green corridors. Additionally, which is what is in this slide, we are also looking into the just and equitable perspective of it. So trying to integrate what are the synergies for development of local communities, the synergies for the development or the securing of electricity for communities that don't have electricity, economic growth, or infrastructure development of specific areas of interest. And then for each of the studies that we do a specific set of selection criteria. And this is done in cooperation also with the local authorities to hear what are the important elements that they would value when it comes to the establishment of green corridors. And I must say, for all the green corridors that we have done so far in different countries, we always look at domestic, regional, and international maritime routes. In India, one thing that has come up as a specific request has been inland waterway routes. This has been added because of a request of the ministry, but also ship recycling and building capacity. This has been brought forward as an important element from a strategic focus perspective of the Indian government. So we look at our data cube and we look at this selection criteria. And with all this, then we create a gross list of potential green corridors. And just to say, when we have done this in the past in other countries, we have had maybe, 8 to 10 green corridors. In this case, we have, I think, 49. So that just tells you about the size of and the potential of the Indian subcontinent to create these low carbon trading routes. So we have both inland waterways, potential green corridors, domestic, regional, we have international green corridors, also green bunkering, so export of these green molecules, and the ship and building and recycling. So this is essentially very much work in progress. It is a gross list. Obviously, not all of this will materialize, but this is a first pass assessment. So what is happening now is that as we are concluding this pre-feasibility phase, we are planning for what we call a consortium incubation workshop. And I have to apologize for the date that it says here, because when I sent the presentation, it was still that date. At the moment, it's going to be in April in Delhi that we will be conducting this consortium incubation workshop. And the purpose of that is to present the results that we have, invite public and commercial actors that could take a role in the different steps of the value chain. So we present the results, we share the potential list of green corridors, and we do a sort of voting. We try to assess which corridors would be prioritized, which are the most interesting, which have the higher chance of actually succeeding, and then make a shorter list that can go further and be mature further. So it is a sort of, I would say, a request of interest from the commercial actors that need to bring these green corridors further. So this is an invitation for the audience here to register your interest if you want to participate in the workshop in April in Delhi. There will be, I think, quite a lot of participants there. So the QR code is for registering interest, and then you would be contacted by the organizers, which probably would be the Ministry of Port Shipping and Waterways. That is all I had for today. Thank you very much for your attention.
Next, I move to the sector where I belong to, the oil and gas side. I have Kaushal Joshi, technical expert from Shell India. Shell, all of us know, right? I mean, they were the pioneers in bringing fossil fuel to the planet. And right now, they are taking major steps and also in the renewables and alternate energies. So over to you, Kaushal. The next 15 minutes belongs to you. And maybe we can take some questions after all the presentations are over.
Good afternoon, everyone, and thank you for introduction. My name is Kaushal Joshi. I'm working as a global principal technical expert in Shell's engineering division. I look after civil engineering, offshore structures, subsea, mat-ocean, pipeline, and I spend good amount of time to make sustainability in design, construction, to the technology deployment as on as like AI. Today, I also have this particular presentation along with two of my colleagues. I would like to acknowledge them. The second person is Naveen. He's an expert for supply chain. He works for contracting and procurement. And the third contributor for this work is Shubhrajit. Shubhrajit is head of corporate strategy in Shell. So this work is a joint work between a technical supply chain as well as the strategy together. In today's presentation, I will be covering only one key message, which is based on the case study that I'll present. We have tried and deployed a new type of construction material, concrete, which we believe has got very low greenhouse gas intensity, so it's very clean. It is affordable. Green does not mean expensive, so it's a clean, it's affordable, and it's very fast in terms of construction. So my entire presentation will cover on a case study of a concrete which is affordable, green, and fast. In my presentation, I'll be using quite many forward-looking statements. So this is just a cautionary note from my company that all the views I present, they are my personal views. This particular case study do not mean that you need to go and do a certain type of investments as well as the GHG practices. So it's a very fine footprint, but it's a cautionary note that there are lots of disclaimer in my presentation here as well. Now, let me switch the gear and by asking you one very basic question. What do you think? What is the most consumed material by mankind? What do you think? What is the most used material by mankind? What do we use? The highest amount? Any thought, any question? What do we use? Sand? Good. Any other thought? Steel? No? Any more? I heard sand, I heard steel. Which is the most used material? Soil. I'm afraid the most used material is water. We use water a lot for a lot of things. Now let me go to the second one. What is the second most used material? And it is almost on the same line that you said. The second most used material is cement concrete. So concrete is the second highest material that we use. But there is a bit of a anomaly with this particular thing. It is the second highest material, but when you look as the entire sector, the construction sector, we believe, is the second highest in terms of GHG emission. So we use a lot, and in order to utilize this material, we also have lots of GHG footprint along with this execution. On the right-hand side of your screen, there is a nice bar chart. It just shows the split between the various type of global CO2 that we emit. And somewhere we focus that a good amount of like 16% of this of CO2 comes out of construction sector. If you split further, this 16% of construction, we see a large portion, roughly 43% comes out of cement. During this week, you heard about decarbonization, but this is one of the hard to abate sector. This 43% of cement in its manufacturing till its deployment, there is lots of embodied carbon which gets consumed. So one of the tasks that we picked up in our company, because we also build our environment and infrastructure for oil and gas, as well as for renewable facilities. So the task was like, let's focus on this particular aspect of construction where we can reduce the GHG footprint. Now, in order to develop this particular technologies, we had lots of bottleneck. Although it is very well known, but there is always a commercial pressure to make it viable. Will it really be affordable to have this kind of sustainable construction, and will it work so that the last user can penetrate and utilize it? So we have a significant challenge in order to get it done. As on now, most of the construction in many part of the world is focused on cost, schedule, because we want to do it very, very quickly. There is always safety, and we have got efficiency pressure to deliver it in a quick, affordable time. And there is a parallel decarbonization challenge. The energy intensive process makes it very difficult to change it. Whether it's a steel or a cement you manufacture, it has got inherent demand of energy consumption. It has got very low amount of renewable resource which gets into it, because construction needs lots of bulk material. It integrates lots of things. and then we go into it. So overall, there is a high emission, which is part of this particular construction segment. And whatever we build, it has to be durable. It needs to be long lasting. So the question was again, how can we have a construction which is affordable, which is green, and which is fast as well, without compromising it? And one of the solution, after having a good amount of brainstorming, we came up with a graphene infused concrete. In one way, graphene is a nanocarbon material. We added into a concrete. Concrete is nothing but cement and water and sand and stone mixed together, but we spiked it with a nano material. The magic happened is that once we add a small portion of a graphene, which is a carbon nanomaterial, into concrete, it reduces the demand of cement into making that construction material. Once we have graphene, cement reduces, and parallelly we have got the benefit of reducing the GHG footprint of this particular concrete mix. Now, there are lots of challenges, like, okay, fine, nanomaterial, but they are not available in the bulk scale where we can utilize it. So the supply chain is always constrained. In order to include it, we need to make sure that it gives the right characteristics of engineering property like strength and durability. It's a very complex way because concrete is roughly, hundreds and thousands of year old material. Now we are introducing a new type of admixture into it to ensure and how we do it. And if you can look into the photographs, it's not very organized and sophisticated way how we do the concrete construction. So how would we bring it? Because there are no easy standards to incorporate it. So this particular photos that you see, they are from one of the site where we have deployed. We were building a kind of a giant compressor foundation. All of you can hear the noise of this hatchback. So this hatchback, there is a compressor out there. So we built a big giant hatchback foundation using this particular type of concrete. Now, knowing all these constraints, we came up with a solution. So the hatchback compressor, which I said, it's right now installed more than 2.5 years. It is built using the graphene infused concrete. In entire process, we ensured that the footprint, GHG footprint, has been much lower than the conventional construction that we had. It was affordable. In our case, the cost of this particular concrete was lesser than the conventional concrete that we use at everyday practice. And it was ensuring that we deliver a high performance. In this case, the strength was very high, the durability was very high, and we also ensured that the execution became very, very fast. So if I may just flash that in a normal case, if you build a cement concrete, it has got embodied carbon into it. But if you use this kind of graphene or a carbon nanomaterial, there is a potential to reduce up to 25% of CO2 footprint. Now, it has been one of the first of kind to use this material for a real industrial scale structural construction. In past, we just learned that people have been using for the paving, but the carbon nanomaterial, bringing it into a concrete for the decarbonization of construction was one of the first kind. And when we implemented it at the Shell Technology Center at Bangalore, we have been doing a good amount of de-risking, how we deploy it, how we ensure that the process just reaches to the required quality and also meets the long-term requirement enforced by the standards and statutory thing. So this was the first of kind that we tried and deployed. Now, if I may just summarize the entire presentation, I've got only 3 bullet points that I can share. In our case, the concrete construction was half of the time it used than a normal construction. So the entire process was 50% faster than the time it would have taken for any other conventional construction. So the construction process, when it reduces time, it gives the benefit of safety, the exposure of workers and laborers. It also gives the bit of a commercial benefit. When you can build some infrastructure fast, it goes back to the user that quickly and it starts building the benefit quicker. The second benefit we had it is when we worked out, the entire process was approximately 62% less amount of raw material that it used for the construction, And the net effect, we found out that roughly 74% of GHG emission were lesser than the conventional concrete that we have used. So it was first of a kind. When we mixed it at our Shell Technology Center, Bangalore, it was deployed for a for a proper HVAC compressor, install it, run it, and now more than 2 years it is out in action. It is still performing. It is meeting those durability criteria, and that we are using. I've got two graphs on the right hand side. One is a bit busy. It shows the time versus the amount of strength, what it gains because of the construction. Once we introduce the graphene, the strength gain became very fast. What it means is that certain amount of targeted compressive strength it needs, it was very fast, and at the half of the time we achieved it. Normally, like this kind of construction, we need to wait for several weeks and months to install and commission. Here it got installed much quicker. The second graph at the right hand bottom corner, it just shows the 3-bar chart to compare. On the left hand side, it just shows a normal concrete that we use. In an engineering term, we call this as ordinary Portland cement concrete construction. Imagine that has got a certain amount of GHG footprint. When we try to use a different type of material, very clever engineering, try to minimize, use the best of the art technology, it can give us some reduction. But once we introduce this carbon nanomaterial into the concrete, we could reduce up to 74% of GHG intensity into the concrete construction. Now, this is a kind of a very positive outcome for my company as well as some of our partners. We have been working with some of the startups who have been partnering with us to develop this particular thing. There are also issues in terms of scaling it, making it large so that it gets deployed to other part of our partners as well as for the industry as a whole. So the first potential use case is there are lots of international projects where we keep constructing, we keep building infrastructure and concrete is consumed. So we have been in talks with some of the international players for the construction where this particular technology can get deployed. The second one is my own company. We build assets, we build projects, and that's where the internal demand comes in. And we have been deploying this low GHG concrete construction into it. And then lastly, the construction and infrastructure industry as a whole can benefit by doing, decarbonizing the construction itself. In a summary, I can say it was one of the first of a kind to try the particular type of construction for the industrial use, like a large-scale HVAC compressor, and we have been able to de-risk this entire technology. It was done at the real industrial scale, a large-scale construction, and it is potential to be used for nominal construction as well as for the specialist construction where you want very quick, affordable, and a low GHG construction that we can have it. I would just leave my last part of this presentation is like we are still working on two aspects. One is the industry standard itself, because the construction industry has been very conventional and it is evolving. So we are working on developing a standard practice so that it becomes mutually beneficial. And second is like working in terms of scalability. So we are partnering with some of the startups, some of the industry segment in order to make it scalable. With that, I would like to thank you all and looking forward for more interactions. So thank you.
That was amazing, right? It's exactly 15 minutes. So if somebody wants a prize for sticking to number, it would be Kaushal. Kaushal, the last speaker today, I have Yogeshkumar Bhola. Yogesh is manager of GAIL India Limited. So, I mean, as India is translating from coal, crude to the renewables, gas is one of the transient fuels which India had identified some years back, at least decades back. And it was great to see in COP 2 years back when the world comes and says gas is transient. So GAIL has been working on producing and moving India into a gas-based economy with targets that which we are doing great. But one of the challenges that transportation across a country as large as India is the energy that's associated with transportation of these gases. So when I looked at the topic on which Mr. Bhola will be talking is how they were able to convert one of those compressors along a pipeline into electrification, I thought that would be something I'm myself very keen to listen to. So over to you. You have the next 15 minutes and hopefully we'll also stick to time.
Good afternoon to everyone present over there. Thank you, sir, your kind introduction. Also, big congratulations to all presentation for the impactful and engaging presentations. As introduced, I am Yogeshkumar working in GAIL India Limited, and I am responsible for energy efficiency and net zero solutions. The topic that we are discussing today is very highlighting, as our topic is replacement of gas turbine drive from the turbine drive. As you know, GAIL India having a net zero plan on 2070. GAIL has enhanced the net zero plan by 2035. In vision, we have already achieved some remarkable achievement, like we have commissioned green hydrogen plant, SS LNG plant, floating solars, wind gas recoveries, and electrification of gas turbines. As you all know, GAIL having a extensive long cross-country pipelines. We have more than 20,000 kilometer pipelines across the India. And here is the three major pipelines that you can see in the figure, HVG, DVPL1 and DVPL2. Along these pipelines, we have total 8 major compressor stations. And among these 8 major compressor stations, we have total 54 number of gas compressors driven by the gas turbines. So the key technical questions that we are going to discuss is why replacement of gas turbine drive with the electric motor? The second, why did we start this project with the turbine A installed at particular location Vijaypur? The third is how we did that as a first pilot project and what we have achieved. Challenges and learnings that we have faced during the executions, and why the electrification is a future. So as I said, HVG is one of the longest pipeline installed in way back 1987 and 88, which was the first GAIL pipeline. Along this pipeline, we have total 28 number of gas compressors stations. We have 4 number of gas compressor stations, and we have selected one of the turbine in Vijaypur stations, that is turbine A. And now let me explain the typical diagram of the gas turbine drive compressor. So the rightmost you can see the centrifugal compressor, which is used to increase the pressure inside the pipeline, and the center one is the power turbine used to drive the compressor by using potential energy of the flue gases, and the first part is the gas generator used for generating the flue gases by combustion of fuel gases. So how it conceived? The old turbine that we have used, overhauling and service cost was, the lead time was 18 to 24 months. The overhauling cost was rising, which was approximately 16 to 18 crores. Comes every 6 years. The volatile fuel gas prices, reliable electrical grid power availability. The state grid power is available throughout the year, where we have converted. The net zero initiative, GAIL is committed to developing our decarbonization capabilities. The last, efficiency. The electric drive is way ahead in the efficiency, which was 15% in the turbine. The second question, why only turbine A? The pipeline hydraulics. Operating hours of the unit. The units having a maximum operating hours are more rewarding to convert. Dependency on electricity, reliability of grid power, and availability of nearest source. existing asset, the book value of existing asset, it should be a older or absoluting. The new turbine retrofit is not feasible. Other aspect, there should be no any combined cycle, because if any heat recovery steam generation is available in the downstream of gas turbine, it will not use for the electric drive. So what we did as a first pilot project, you can see the old schematic that I already explained, compressor, power turbine and gas generator. In a new scheme, we have replaced gas generator and power turbine by keeping existing compressor as it is. You can see here electric drive of 3.6 megawatt motor and the Flander gearbox in the center. As a major milestone, we have started the feasibility study, which was most important in May 23, tendering and order placement by July 23, drawing approvals February 24, manufacturing supply of major items July 24, site removal of old turbine September 24, and installation and commissioning of new major items December 24. So details of major equipment, the first you can see the electric motor of capacity 3.6 megawatt with having RPM of 1500. Then we have the gearbox which will convert 1500 RPM to 12,000 RPM for the compressor. The third one is VFD, variable frequency drive, used to control the variable loads of compressor. The fourth is switchboard, used to power the electric motor. And the fifth was automation and control logics. The scope of GAIL, the total site execution done by the GAIL in-house team. The execution is involved 4 steps. First is removal of old gas turbine. Second was erection of foundation. Third was installation of major equipment. Last was the alignment. As a removal of gas turbine, we have removed gas turbine, power turbines, associated auxiliaries, skid, stacks, filtration, fuel lube oils, controls, and F&S systems. For foundation, erection of mechanical and civil items, base plates, stiffeners, 1000 plus meter square, weldings, which was designed for dynamic and static loads. The third was installation of cable laying of approx 1.8 kilometers from VFD to motor and motor to substation. Partition of HVAC systems, installation of motor, gearbox, VFDs. Last, alignment of the gearbox with reference to the compressor and alignment of motor with respect to the gearbox. Here are some photographs of site removal activities. You can see here the old gas turbine in the first photographs. Then we are removing the stacks, air filtrations, dampers, base frames. The second was the erection of foundation. You can see a reinforcement, base plates, UC beams, pockets, and the civil concretings. The third part was installation of major equipment. You can see the installation of gearbox, motor, VFD, partitions, and couplings, and finally alignment. Apart from the site execution, the major part was logic and control system, as the first logic and control was for the gas turbine and the compressor. But now for the new system, it was for electric motor, gearbox, and compressor. So we have prepared logic and interlocks, 190 plus input and outputs, logic flow diagrams, hard and soft cables between VFD to motor, motor to VFD, and from board to the PLC at control room. And we have prepared HMI panels for the final graphics. You can see some HMI snaps. In first you can see compressor, second in motor, gearbox. So here GAIL's first electric drive is looking like. You can see the compressor is totally undisturbed, and which is inside this green enclosure. The second blue color is the gearbox, and that white color is the electric motor. So key highlight was we have conducted 100 plus team meetings for the document review and approval, 250 plus critical document reviews for the feasibility study, 50 plus interdepartment meetings for HAZO, technical specification and gap analysis. Complete site execution done by the in-house team. No single PMC or consultancy was hired. We have saved 30 lakhs for in-house machining by the help of our lathe machine and drillings. 90 plus percentage site items designed by the in-house team. Now let's talk about the merit of electric drive compared to the gas turbine. The first is heat dispersion, reduction of hot gases at 55.8 TPH, right, with the temperature 571 degree. The second and most impactful, reduction of CO2 emission, the tune of 12,000 ton per annum. The capex cost for the project was around 17 crores. We have lowered the one-time cost about 90% of lower to the turbine. Significant boost in the efficiency, which is more than 75%. We have payback period 9 to 10 months. Easy to start and stop compared to the gas turbine, so operational flexibility is increased. Reliability of grid power, so reliability and availability is increased. So here is the efficiency aftermath. The motor gas turbine, gas compressor to gas turbine to compressor efficiency is around 33%. Electric drive efficiency is 80%. Transformer to compressor. Turbine we have replaced, which was Ellison turbine. Efficiency was 24% only. That is the calculation. Now coming to new drive, complete train efficiency is 76.5, which is more than 75%. It is a 3 times than the older gas turbine. Now talk about OPEX cost saving. The fuel cost for the gas turbine drive per annum was 23.67 crore. For the electric drive, it is coming to 7.84 crores. Overhauling, service and maintenance cost for the gas turbine drive per annum is 7.15 crores, and for the electric motor is 0.22 lakhs only. So per annum the cost saving is 22.97 crores. As I said, the total capex involved is 16.45 crores. The per day benefit is 7.66 lakh. The capex 16.45 is only for the first electric drive because we have already substation and grid power was available. During this execution, we have faced some challenges and learnings. The first major challenge was that the existing gas turbine foundation was unsuitable for the electric motor and gearbox. We have addressed this by constructing a new foundation without disturbing the compressor, also accommodating the dynamic and static load of the motor and gearbox. We have used our 20 precision measurement tools to fix elevation, site offset, diagonals and take center to center distance. As the foundation was totally irreversible, a millimeter deviation could have jeopardized the entire project. The second is lube oil and seal oil. Another major change was complete modification of lube oil and seal oil system. The entire system was driven by the power turbine and gas turbine. Now it is for the gearbox and motor compressor. In a first drive, the main oil and seal oil pumps was directly mounted in the power turbine. But in the new drive, we have make it independent pumps. Here you can see some side photographs. The major gearbox, the third challenges was specific anchoring bolts for gearbox and motor. The major gearbox and motor highly precision anchoring required with tolerance of 1 to 2 mm only. We have used L-type 8.8 grade bolts and we have directly welded to the underlying mechanical structures to compensate the dynamic, static and cyclic load of the motor and gearbox. The next one is the heat load of VFD was not sufficient for the existing substation. So we have constructed participation and we have dedicatively installed our HVAC system. I am glad to inform that recently, before 20 days, we have completed 1 year of commissioning and we have run more than 6500 running hours in a single year, which is highest ever in the
We're
turbine.
on time now. Yeah. Can you wrap up a bit?
So this is the last slide. So why electrification is the future? The target is 50% of renewable energy by the 2030, which will available in a reasonable prices. The success of this pilot project reflects the brilliance of our in-house team achieved through a seamless collaboration, expertise, as it was done by without any PMC. Finally, I would like to thank you all. Thank you very much to my company, GAIL India Limited, who has provided me this opportunity. IEW for providing me this platform at such a young age. To my career, this will definitely help to a career. Thank you, everyone.
So with that, we come to the end of this session. Thank you all for your attention.